Hello, and welcome to today's webinar, State-of-the-Art Ultrasensitive Imaging Technologies for Microscopy, Choosing the Best Solution, presented by Andor Technology and hosted by Photonics Media. I'm Owen Brock of Photonics Media, a brand of Lorne Publishing, and publishers of PhotonicsSpectra, Biophotonics, and Europhotonics magazines. You can find our website at www.photonics.com. Our presentation today is from Dr. Colin Coates, who is the Imaging Product Manager and a Senior Scientist for Andor Technology in Belfast, Northern Ireland. Dr. Coates has a PhD and postdoctoral research background at Queen's University of Belfast, focusing primarily on the use of laser spectroscopic studies to elucidate the detailed photophysics of useful metal-centered complexes. He has also worked in R&D developing novel DNA microarrays. Thank you for joining us, and please begin your presentation, Colin.
Thank you. Welcome everyone to this webinar. It's called Ultrasensitive Imaging Technologies for Microscopy. So really the rationale for presenting this presentation is it's an acknowledgement that there's a number of scientific imaging camera technologies out there from which to choose. So I wanted to give something that was geared towards low light fluorescence microscopy in particular. And so that kind of sets the agenda. So first of all, I'll cover a few basics of what is sensitivity. Then I'll cover three technology types. CCD technology, we'll spend some time on EMCCD technology, that's Electron Multiplying CCD technology. And then we'll talk about the newest type of technology to hit the market, which is scientific CMOS. So we'll gather these technologies together in a section which compares them specifically, and then we'll finish off with a few application recommendations, just throwing a few applications up there and talking about the most appropriate technology type, given what we've discussed. Okay, so pressing on. First of all, here's a portfolio of our low-light imaging cameras. It's a good representation of the technologies that do exist. We cover a lot of bases with our own portfolio. We have cameras here like working from even left to right, the Luca, which is a price performance EMCCD, single photon sensitive USB, and a kind of a moderate frame rate. The iXon, which you can see next to it, is a very deep cooled, back-illuminated traditional slow scan CCD. So they would still have a lot of usage in applications, more usually that require longer exposures. Next to that is the Neo sCMOS, and we'll spend a good bit of time talking about this technology. Beside that is our market-leading EMCCD. It's the Xon. The Xon line has existed for more than 10 years now. As I say, it's currently the industry-leading platform, and it's really a very, very high-performance version of electron multiplying CCD technology. And finally, here we have the Clara. So the Clara is based on a interline CCD technology. So it's been kind of a ubiquitous technology for microscopy, for fluorescence microscopy, especially for about more than 10 years now, 10 to 15 years. There's good reasons for that. It's a very sensitive CCD. It's got very appropriate pixel size for microscopy, and it works at fairly reasonable speeds, which have suited live cells. So we'll talk about how these various technologies hang together. And in particular, I guess the three that I'll spend more time on are represented here: the Neo, the Xon high-performance EMCCD, and the interline CCD as represented by the Clara. Okay, so just first of all, a general comment on when we need sensitivity and why we need sensitivity, because this generally drives the rationale for using Andor cameras. So there's a number of reasons that are relevant to various types of microscopy, various modalities of microscopy. The top one here is about low dye concentrations right down to the single molecule level. So single molecule detection, for example, would be the biggest market for electron multiplying CCDs. A good majority of EMCCDs that are sold from Andor will actually find their way into one single molecule technique or another. But even in live cell imaging, there's often rationale to push dye concentrations to lower amounts, for example, to not affect the physiology of the cell process you're trying to study. Then you move to faster frame rates. So with faster frame rates comes shorter exposures, and that means with any given exposure you're going to accept less photons, therefore more of a need to counter that with higher sensitivity from the camera. The next point I'm getting at here, where I say high photon loss or photon rejection, really corresponds to modalities of light, or sorry, modalities of imaging that are designed to reduce the amount of background photons in the image. So examples there would be the turf or the spinning disk confocal. So spinning disk is great for giving fantastic confocality, rejects a huge amount of out of focus background light, but it does in turn yield a very, very low light signal typically. And again, you would need very highly sensitive cameras to counteract that. Lower excitation power is a much cited one, a very important one, especially in live cell measurements. You want to limit the rate of photobleaching of the fluorescent dyes. You want to especially limit the rate of phototoxicity to the living cell also. So again, lower excitation power means a lower photon flux of emission from the dyes, and again, an argument for sensitivity. Even greater magnifications, where you're spreading the photons from a point in the sample over more pixels through the greater magnification, means that any one pixel receives fewer photons. And at the bottom, I'm kind of getting at situations where, through necessity, given the experiment type, you may just naturally be looking at a dye, for example, which has a low quantum yield of emission, or even if you're doing Raman imaging. Raman's a very inherently weak technique. So we've talked about why you need sensitivity, so let's talk about the fundamental parameters of sensitivity in a camera. So really, if you break it down, there's two key parameters. The first one is very, very commonly recognized. It's the quantum efficiency. It's the efficiency at which the pixels will accept incident photons and convert them to useful photoelectrons. And that's wavelength dependent. And every spec sheet you'll see for cameras shows a quantum efficiency graph versus wavelength. Then we have the noise floor. It's a very, very important parameter. So it's really, the representation here is of an object sitting in grass, which is a reasonable depiction of what noise is. The higher the noise floor, in many ways it's the instrumental noise detection limit. The higher the noise floor, the more unlikely you're going to be able to discern a signal sitting on that noise floor. So a sensitive camera must really be designed to ensure that each of these parameters are optimized. And then when you break it down even further, so this is a simplified pictorial representation of the noise. So just take this as being whatever, a vesicle 20, 30 pixels across, and this is an intensity profile through a row across that emitting object. So it's assuming a very, very low level of background photons. So what you're left with is the noise floor of the detector, which is the read noise and the dark noise. The read noise is a function of usually the readout speed. So the faster the frame rates, the larger the read noise. The dark noise is a function of the cooling and also of the exposure time. So the deeper you cool sensors, the lower the dark current, and the longer the exposure, the more time you're given that dark current to build up, resulting in a dark signal, therefore dark noise. Then I'm showing here at the top of the signal a representation of shot noise variation. So this is kind of a certainty. Even the ideal detector would have shot noise variation. It's a function of just the pixel to pixel or frame to frame variation of the photon signal. Higher quantum efficiency, incidentally, will result in a larger signal to shot noise ratio, and that's one way to exert some control over that noise source. So first of all, talking about CCDs, how we would reduce noise in CCDs, and that's depicted here. So this is taken the Andor interline CCD that I mentioned. With this camera we actually have a unique 1 megahertz mode, so typically these interlines are read out at 20 megahertz or 10 megahertz. We've actually inserted a 1 megahertz mode specifically to offer the ability to reduce the read noise when you don't need to go at very fast frame rates. So that's pretty much what I'm showing here, and it's a good illustration of the effect that slowing down the readout rate on CCDs can have. So this is the modality here was the confocal spinning disk, deliberately to reduce the amount of background photons to better illustrate the effect of read noise. So I'm showing here the 20 megahertz mode versus the 1 megahertz mode. So it's reducing the read noise when you slow down from about 5.5 electrons to about 2.4 electrons. And this is the same intensity scaling, and you can see the positive effect that slowing down has on the noise floor. You can see much more contrast from the features across the same exposure time. So that's obviously an issue of CCDs, that when you want to go faster, when you have applications that require faster frame rates, then you're limited by the fact that the read noise increases quite significantly when you read out faster. So as I say, about more than 10 years ago now, we launched the Electron Multiplying CCD to the scientific market. The market leading camera here is called the Xon line. Our latest version is called the Xon 3. So I'll talk a little bit about EMCCDs. So really they were designed to overcome this read noise detection limit, which can be considered the primary detection limit of a scientific camera. And they can overcome this, importantly, at any readout speed, and they can even be single photon sensitive. So you could have done this with intensified CCDs before, but you would never have got high quantum efficiency. With CCDs, what you can combine is the 90% quantum efficiency of the silicon itself with the ability to still be single photon sensitive, to amplify even a single photon incident on a pixel into a size that means the read noise is no longer an issue. It's practically negligible. So importantly, you can do this at fast frame rates. It doesn't matter that the read noise increases significantly at fast frame rates. We have enough amplification power to overcome the read noise no matter what the frame rate. So that's really the beauty of EMCCDs. This is a very simple animation, and what it's really trying to point out is the architecture of most EMCCD. In fact, every commercial EMCCD on the market pretty much has this architecture of a frame transfer sensor where you would expose the image, rapidly shift under the mask, and while you're reading out, another image builds up in the open exposed area. But really the unique part to the EMCCD is this insertion called the gain register. So as every pixel is read out, it travels through the pixels of the gain register, and that's where the amplification process takes place. This next animation is really trying to illustrate what's happening in a couple of pixels of the gain register. So basically the principle is that this will be voltage in the y-axis. There's a stage where charge is transferred and a lot higher voltage is applied than is necessary just to transfer the charge. So this creates a high electric field, and with that comes a probability of creating an extra electron. It's a process called impact ionization. So the probability of creating an extra electron is not a high probability, but when you do this in serial over more than 500 pixels, then you can generate overall amplification factors of more than 1,000 times if required. And this is a simple demonstration of the EM gain in action. This was just done with a wide field fluorescence setup, so there would even be some significant background light in here. And what you have is a read noise dominated signal when there's no gain. When you apply the gain, everything is amplified well above the read noise. And when you scale then on the signal, you don't see the read noise anymore, and that's what's happening. The read noise itself hasn't changed. It's just that the signal intensity has changed dramatically, and the read noise is now negligible. There is one downside to EMCCDs, so you don't get all this amplification without a price. And this is important for the comparisons we'll talk about later on. You have this multiplication factor as a function of the probability of amplification. So this is well modeled, well theorized, and actually well measured as well, and published in papers. The effect of multiplication noise is to increase the shot noise variation by a factor of square root 2. So we'll talk about that later and the effect that it has on the overall signal to noise of EMCCDs, especially in a comparative sense. Now it's worth mentioning there is a way to overcome this multiplication noise, and it's embedded within the ability of the EMCCD within the software. You'll find a mode to do this. There's what is called single photon counting. If you're counting photons as binary events, it's either there or it's not, then you don't care by how much has been amplified, and that's actually a mechanism to gain that root 2 noise back, or sorry, root 2 signal back. So the the Xon EMCCD range is represented here. By far the biggest seller is the one shown at the top. It's the Xon 3897. So this is a 512 by 512 frame transfer format, back illuminated. It's fairly large pixels, but these pixels are certainly not prohibitive for applications like single molecule detection. And it's a good balance of extremely low background noise and frame rate and sensor format. So it's been a very, very popular sensor within the EM range. Next here is the Xon 888. So it's a larger field of view. It's about 2.5 times larger field of view than the sensor above. It's back-thinned again. What it sacrifices is the frame rate. It's about 9 frames per second. It's about a 13 micron pixel size. It's also, to be fair, one of the more expensive cameras of the range. You tend to pay more for the greater silicon involved. Now the next one here is kind of more of a niche camera. It's the Xon 860. It's a lot smaller field of view. It's 128 by 128. The pixels are really quite large, 24 microns, but it does go fast. It does 515 frames per second. So it's directed towards applications which really, really need sensitivity at very fast speeds. The bottom one here is the Xon 885. It's based on a sensor from a different supplier from the cameras above. It's not a back-thin sensor. It's called virtual phase, the sensor finish, and it offers about a 65% max QE. It is a very flexible sensor in that it's 8 micron pixels, so you can use this more effectively in live cell microscopy and oversample the diffraction limit quite adequately. And it reads out fast in that it's 1 megapixel, which can do 31 frames per second. If you then 2x2 bin, for example, to create 16 micron pixels, it will do about 60 frames per second, so it does have quite a good speed advantage on its side. So what I'm showing here is the QE curves of the range I was just talking about. So the BV curve in the solid green is the back illuminated curve, and that's the one that's most commonly ordered. You can get what's called here a BB curve, which gives better performance in the blue range, and that VP refers to the Xon 885, that virtual phase sensor finish that I was talking about. So in our Xon EMCCD, it is very important to minimize the amount of thermally generated electrons within the silicon itself of the sensor. So this is one of the things the Xon has always done really, really well. It's especially important in EMCCDs. I mean, it's important in CCDs in general when you want to go to longer acquisition times. But even for a short exposure in an EMCCD, it can have a new relevance to applied cooling. I'm showing here a 30 millisecond exposure, and I've amplified by probably about 1,000 times gain to really bring out the background events. And what you see at minus 30 are all these white speckles in the image. So these are amplified single thermally generated electron events, dark signal events, or dark current. And that's more relevant in an EMCCD because normally in a CCD, single events like that at short exposures would be lost in the read noise floor, wouldn't really matter. With an EMCCD, because of this amplification mechanism, the same mechanism that's applied to amplify photons is also amplifying these thermally generated electrons as well, so cooling carries a new significance. So you can see the effect that going to minus 85 has on the amount of thermally generated background there. So that makes the instrument detection limit so much lower. We've overcome the read noise through the EMCCD. Now we're minimizing what would be one of the remaining detection limits, which is the thermally generated dark current. So that's just showing a line profile from an image at 3 different temperatures to show you the extent of how you can reduce these thermally generated spiky dark current events. Similarly, there's another noise source called clock-induced charge. So again, clock-induced charge would happen in CCDs as well. They happen primarily during the vertical shifts during readout, the parallel shifts. It's a very similar mechanism that yields clock-induced charge as is applied in a positive sense in the gain register I talked about. It's applying a voltage, generating an electric field to transfer charge. Here it inadvertently creates an electron very occasionally, but that can mount up, and if you don't have very good control, and if you don't have very good control over how you're clocking, clock-induced charge can be a big problem. One of the real advantages we would offer is the ability to effectively overclock the sensors. That can drastically reduce the amount of clock-induced charge. So I'm actually showing you two situations there in a very, very low light experiment, which is single photon counting, where clock-induced charge, if you let it be too high, can be very, very damning on the amount of contrast in such an extremely low light experiment. Another mode I wanted to mention here is called crop mode. It's a mode in the Xon and a few other cameras in our range actually that lets you drive a lot more speed out of regions of interest. So here I'm showing two frame rate tables, and I've circled the 128 by 128 region of interest. So when you do a standard region of interest, if you're not in crop mode, for example, you would get here 132 frames per second if you were starting off from the 512 by 512 sensor. However, if you go into cropped mode, the same region of interest can pretty much treble your frame rate. Now, the trick to this is we're basically fooling the sensor into thinking that it's just 128 by 128. It reads out as if it's only that size, and therefore it's not really acknowledging that there's other pixels there to get rid of. So when you're in the standard means of reading out a smaller region of interest, there will be invariably light falling on the neighboring pixels. Even if you don't want them, you still have to transfer the charge out and dump that charge somehow. In crop mode, we're just ignoring that step, but then there's a condition. That means you have to physically mask off the pixels that you don't need. Otherwise, charge is going to build in them and then transfer into your image area for the next image in the sequence. So that's where you have to use an accessory. What we offer for this is an accessory called the OptoMask. It works extremely effectively. It's designed for microscopy. You can see it there on this slide. It's an insertion between the output of the microscope and the camera. And you can see those four little blade adjusts. You can adjust these quite readily when running in real time and visualize on the screen the amount of masking you're doing. So you can actually set up your ROI using those blades and then match it using the ROI crop mode function in the software, and away you go. So that's a very, very handy method for physically masking and allow you to basically, in some cases, treble or even greater factors your frame rate in ROI mode. There's another feature we implemented in the Xon called OptoQuire. So this is in recognition that the Xon, while being one of the most flexible cameras on the market, you can adapt it to quite a number of different application scenarios. But with that comes somewhat of a burden of knowledge. There's a lot of parameters you could adjust to tweak the camera in different ways. And it's acknowledging that not everybody would have that level of knowledge. So we try to remove that burden from people. In the software, we've put in an OptoQuire setup. So when you press OptoQuire within the setup dialog, it sorry, 1 second, I'm getting a strange message on screen here. When you set up OptoQuire, when you hit OptoQuire within the setup acquisition dialog, the OptoQuire menu that you can see in this slide then becomes your new acquisition dialog, and within that there's some simple descriptions of how you might want to optimize the camera, either for speed and sensitivity or dynamic range and speed or fastest frame rates where nothing else matters. So you can see some examples there. And then what happens, the camera's kind of optimized behind the scenes for you. It tells you what has changed, so you can actually learn a bit about how it's optimized through this mode. And then if you want to create further modes that we haven't covered that are specific to an application you have in mind, it gives the ability to create your own user-defined modes and save them with your own descriptions. So that's OptoQuire. There's another feature called count convert. So there's been a few customers over the years have asked us, how would we back calculate when you have a signal in counts? How do you back calculate to estimate either how many electrons were were generated in the original pixel of the sensor, or even take it a step further and estimate how many photons were incident on that pixel. So we've put this into the camera. This back calculation is now done automatically for you, and you can I've kind of shown an illustration of how of the calculation steps there that are relevant to an EMCCD when you do this back calculation. So you can now just select this in the software. You can either do it real time or as post-processing. In post-processing you would keep your original data in counts, and then you can generate a copy, for example, either in electrons and photons, and therefore keep both sets. Or you can do it in real time, just choose up front whether you want to display your data in electrons per pixel or in estimation of incident photons per pixel. When you choose photons, you can see that little dialog there. When you say convert to photons, you have to enter a detection wavelength. So that step is taking the quantum efficiency into account when estimating the photons, and since quantum efficiency is wavelength dependent, that means you have to enter a wavelength. And naturally, the more narrow band, say your emission filter, the more accurate that final step of estimation would be. So that can be useful for some applications. For example, we've had inquiries from one of our main markets, which is super resolution microscopy, where it can be convenient in order to quickly estimate the localization accuracy of a PAM store measurement to have a quick reading of incident photons per pixel. So now I want to cover the sCMOS technology. So this was released to market in the NEO about a year ago. And really the rationale of this technology is to combine a lot of performance parameters in one and not have to worry too much about trade-offs. So as I mentioned in CCDs earlier, you very much have to worry about trade-offs. For example, when you want to go faster, you have to worry about your read noise increasing, so there's very much a trade-off there. There's other trade-offs as well, like when you go to smaller pixel size, your dynamic range would be hit. So there's sufficient technology built in to this sensor which we're employing in this scientific CMOS to counteract many of these trade-offs. Basically we're getting a very low noise, naturally low noise sensor that does not require multiplication like EMCCDs. It's capable of very, very rapid frame rates. It offers a wide dynamic range through a dual amplifier structure I'll talk about. It's got quite high QE. It's got a high resolution, and it's a 5.5 megapixel sensor. With that comes a large field of view as well. And importantly, it's got a rolling and global shutter readout mode as well. So I'll talk more about those two readout modes which are particular to CMOS technology later on. So a quick performance overview of the key specs. It's 1 electron noise at 30 frames per second. So that's getting down towards EMCCD levels of effective sensitivity. It is a high resolution device, as I mentioned. It's 5.5 megapixels, and we chose a 6.5 micron pixel size when we designed this. In an acknowledgement primarily of the fluorescence microscopy market, it's a good balance of pixel size. If you go too large, you're not oversampling the diffraction limit sufficiently. If you go too small, you don't collect enough photons, which would limit your signal to shot noise, and also it would reduce your well capacity of the pixel. So 6.5 microns we decided is a good balance for this application in particular. I'll show you later on why it can be important to deep cool. We've chosen a vacuum architecture. It's one of our core companies, our core strengths with Andor is to do deep vacuum cooling. We felt it was just as important for scientific CMOS, if not more important, to effect some deep cooling. The high dynamic range architecture I'll talk about later on as well. And we also put on a 4 gigabyte on-head memory buffer. This facilitates faster kinetic series bursts. Also important, we spent a lot of time in developing this camera in looking at the image quality. There is more that you have to do to CMOS technology compared to CCDs or EMCCDs to make the image quality acceptable for use. It's not necessarily a negative thing, just means it requires more effort in the camera, the intelligence of the camera, to normalize some fixed or even variable offset variation, for example, and I'll talk in more detail about this, to then flatten out the background and make it the type of background you'd be used to in CCDs. So this is a very important facet of what we did. And there's innovations there like the dynamic baseline clamp. We have pixel level offset compensation maps, and we also have this optional spurious noise filter. The quantum efficiency is approaching 60%. and it's got a very good, naturally good red response, and I'm showing it here versus a lot of the common dyes, including some of the more red-shifted dyes which are becoming more popular to shift away from the autofluorescence of living tissue. As I mentioned, CMOS you have to start concerning with the readout modes, things you wouldn't necessarily have to concern with CCD or EMCCD technology. Now, normally in CMOS devices, you would, within the sensor, be either hard locked into what's called rolling shutter or global shutter. This sensor is quite unique actually in that it offers both. So we have a simple selection in the software and in the SDK that you can now choose just between rolling or global shutter readout modes. So a more common method of reading out in CMOS technology is with rolling shutter. And I'm trying to illustrate that with this sequence of images, which isn't an easy thing to do unless I have a whiteboard in front of me, but we'll give it a go. So basically, the sensor is split in two across the middle. That dashed blue line across the middle represents where there's a readout split in the sensor. So what happens at the exposure start is there's like let's call it an exposure start front or even a readout front, which moves from the middle outwards towards the top and bottom edges simultaneously. Now, even at the fastest speed of readout, it takes 10 milliseconds for that readout to start completely. So that means the row at the middle will start its exposure 10 milliseconds before the row at the top or the bottom. Then you'll have your exposure time, and then you'll have your readout. So the readout also happens from the middle outwards. So you have the middle rows ending their exposure, potentially even starting their next exposure if overlap mode is selected, and that's a possibility. But I'm trying to make it simple here. So let's just say this is a single image and rolling shutter. So this is the end of the readout. It again happens from the middle, and it takes 10 milliseconds for the readout front to move from the middle to the extremes. So while every row or every pixel in the image has had the same overall exposure, it does mean that the middle rows started and ended their exposure 10 milliseconds in advance of the rows at the edges. So that's rolling shutter. Now, in reality, this can be used for a great many applications, and we'll talk about that in the next slide. But we felt it was important to also offer, given the variety of application conditions we want to apply this sensor to, and even within a single lab, you may have applications, or even on a single setup, you may have applications that will favor one type over the other. So we made very sure to put in global shutter. Now, it's a mode which is more similar to what you would recognize in, say, an interline CCD. It's where you will simultaneously start the exposure for every pixel. The exposure happens, and then simultaneously the exposure ends on every pixel. So that's more aligned with what you might recognize with an interline CCD, even close to what you would find on a free and transfer CCD. It's a simultaneous start and then a rapid shift into, say, the readout area, and that's the end of the exposure, and your next exposure can immediately start. Even while the previous exposure is reading out, you can immediately start accumulating your next exposure. So that's all there in the architecture of the chip. So as I said, we felt it was important to offer both. Now, I'll be frank, there's a sensor launched this week from one of our competitors. It's offering a little bit higher quantum efficiency, but what it sacrifices in doing so is global shutter. So it's worth bearing that in mind. Now, so that's all a bit of a hard thing to wrap your head around, so I'm trying to give some guidance here as to when you would choose rolling shutter, when you would choose global shutter. So you would use rolling shutter when you do not so much require to have exact correlation in time between two separated regions in the image. So say you were doing vesicle tracking or looking at a calcium wave propagate through a cell, it's not so important to have global shutter mode. You'll be temporarily oversampling the rate of movement of whatever you're tracking anyway, and the amount of distortion that you would encounter is quite negligible. In fact, it's usually sub-pixel. So rolling shutter can be used perfectly adequately under such conditions. It's worth noting you will achieve your lowest possible read noise and your fastest possible frame rates with the rolling shutter mechanism. So global shutter is there to acknowledge there may be some applications that do require you to have better time correlation between different regions of the image. So if you need that, given that the center of the chip starts its exposure 10 milliseconds shifted from the extremities of the chip, you won't get within an exposure that correlation in time between regions that are removed from each other in the image. So that's where you might have to concern more with having the global shutter at your disposal. There's also conditions in some applications, more so in physical science, but you may find some conditions in life science as well, where you will want to synchronize the exposure start to be in close proximity to a short pulse of light. And there it's critical to have a global shutter readout mechanism. And the example I've given here is actually more in physical science. It's called particle imaging velocimetry, PIV. So there's a dual amplifier architecture in the sensor. This is what gives it the ability to extend dynamic range beyond what you might expect for such a small pixel device. So in interline cameras, dynamic range is kind of limited. Here we have this dual amplifier architecture, which means you can extend dynamic range. You can simultaneously maintain the very, very low noise of down to 1 electron while allowing access to the full well capacity as well, and that's what makes this architecture quite unique. So here's an example here of just it was a LED illuminating a slide, and you can see a region there where there would be pixels sampled by what's called a high gain amplifier, which gives you the lowest noise, and then there's other pixels which are samplified by a low gain amplifier, which has higher noise, but lets you access the well capacity. And since the signal is so bright, it doesn't actually matter that the noise floor is a bit higher. So the sensor makes a decision basically on a pixel by pixel basis. If you're above a certain threshold, it lets the amplifier reading go through that was from the low gain amplifier, therefore more suited to brighter signals. If you're below a certain threshold, the camera makes a decision to let through the low gain reading of that pixel, sorry, the high gain reading of that pixel, the lower noise, which is more suited to the weaker signal. So I'll just skip through, I'm conscious of time. I mentioned we're quite concerned about the doing enough to clean up the image to make it more recognizable, let's say, when you compare to CCDs and EMCCDs. So with CMOS in general, you have to be very conscious of fixed pattern noise, much more than you would with CCDs. If you didn't apply real-time compensation in the intelligence of the camera itself, you would end up with quite a messy looking background, frankly. Now, fortunately, this fixed pattern noise is a constant. We can map it quite well and normalize it, so we actually hold compensation maps at the single pixel level, which gives us a much better image quality. And we hold these maps for a variety of speeds and gain combinations and cooling temperatures. So there's a lot of information stored in the NEO to give you better background uniformity across a number of conditions. Here's another thing we've implemented. It's called the dynamic baseline clamp. So basically, as any camera would be actually, all signal sits on a deliberate electronic bias offset. It doesn't carry noise itself, but it is subject to some drift, especially when you're reading out fast, and the CMOS technology is no exception. So we've implemented a technology which, on a row-to-row basis, measures any drift of the bias offset on which the signal sits and in real time corrects for it. So that is necessary to ensure not just better image quality, it gives you more quantitative stability of the baseline during a kinetic series or across the image. You know, if you're doing a kinetic series, you don't want to have, you don't want to think that the baseline on which the signal is sitting is varying as well. If anything's varying, you just want it to be the signal itself. We've also implemented, as I mentioned earlier, a vacuum architecture with the NEO. We felt this was very important to facilitate not just the cooling but also heighten the protection of the sensor as well. That enables us to give a 5-year warranty, which we would quite typically apply across our vacuum cameras on the sensor enclosure itself. So as I mentioned, we have done a good job. We're very proud of the fact that we've spent that bit more time concentrating on image quality. Here's a comparative image here of us versus a competing sCMOS. So you can see the level of flattening we've exerted due to the offset compensation and also our dynamic baseline clamp in bidirection. The cooling, as I mentioned earlier, we felt was very important to address with CMOS technology. Dark current can typically be very high in CMOS, so we felt it was important to pay attention to cooling. I'm showing that here with a 2-second exposure. So this is the same sensor type at -30 versus +5 with the same relative scaling in each case. You can see the amount of additional noise that comes from the dark current over a 2-second exposure if you don't cool. So if you plot that out as noise floor against exposure time going up to 2 seconds, you can see the compromise that you can affect to this low noise advantage if you don't cool even over 2 seconds. So the NEO would stay at about 1 electron and not shift from that because the dark current is negligible over this exposure range. However, if you only limit the cooling to northwards of 0 degrees, the dark current would contribute much more significantly even over relatively short exposure times. So we felt it was better for greater application flexibility to impose this cooling. So I mentioned bulk dark current there. So what I'm showing here is hot pixels. So this is a reflection that the dark current really is a distribution, just like read noise in CMOS is a distribution. Dark current is also. There are a tail of pixels which will have higher dark current than the average, and that's what's being reflected here. So this is a subarray of the sensor, and you can see the difference in the amount of hot pixels when you cool the device. You can pretty much cool them into being usable pixels again, whereas when you haven't cooled these pixels, either you leave them like that or you need to compensate for them. So you can have a situation where if you need to compensate them to flatten them out and not make them look hot, you'll have to compensate many, many thousands of them across the entire sensor. Whereas if you cool, you don't actually have to do that. They can stay as usable pixels and don't have to correct them. Even with a 30 millisecond exposure, you can see a 1 megapixel subarray here. You can still see, even with 30 milliseconds, a contribution of hot pixels if you fail to cool. So I want to spend a few slides here just comparing technologies, because this is kind of one of the main points of debate over these past number of months. There's been a number of publications printed. I feel that they've been printed each with a certain agenda. I'm trying to give a more balanced view as to how these sensor types we compare, and bear in mind Andor offer all these sensors. So I've broken this over a number of camera parameters, and I'm comparing the Sony interline. This is this ICX285 interline CCD that I said was ubiquitous across fluorescence microscopy. I'm comparing EMCCD technology in general, and I'm comparing the sCMOS. So where the sCMOS tends to win out here is in the overall size of the sensor. For your money, you're getting a bigger sensor. You're getting many more pixels than you would say with an EMCCD or with a Sony interline. The pixel size, as I mentioned earlier, we decided to keep for the reasons I described to about 6.5 microns. The frame rate with Sony interlines tends to be around typically 11-12 frames per second at 20 megahertz, so it's quite a modest frame rate. With EMCCDs, the main point of the technology was to do single photon sensitivity at speed, so you can get quite decent frame rates from EMCCDs. The CMOS, you push it very, very fast. Now, in there lies a number of challenges. If you went 5.5 megapixels at 100 frames per second, that's a horrendous amount of data to deal with, and there's a lot of challenges there even with the PC, which you would need. But the possibility is definitely there. For most applications, you probably get away with more sustained frame rates of about 30 frames per second. The read noise is one of the areas where the sCMOS excels. So it's about 1 electron at 30 frames per second, about 1.4 electrons at 100 frames per second. So bearing in mind we haven't had to amplify, the sCMOS is very, very good. However, I have highlighted there the negligible read noise in EMCCDs. That reason right there is the reason that most applications that have used EMCCDs to date will probably continue to benefit from a back-thinned EMCCD. That act of having a negligible read noise is surprisingly significant, even compared to a one-electron sCMOS device for very, very low light applications typified by single molecule detection. Quantum efficiency in this we've brought up towards 60%, so we try to align closely to the Sony interline. We haven't done a bad job of that at all with the sCMOS. With EMCCDs, you have quantum efficiencies ranging between 65 and 90%. Now, what is worth mentioning there is the effective quantum efficiency of EMCCDs is actually about a factor of 2 lower than this if you haven't taken measures like with single photon counting to overcome the multiplication noise. So that feeds into the comparisons, the signal to noise comparisons, which we'll be talking about. Dynamic range, again, because of this dual amplifier architecture. So we've taken a pixel that has the same size as the interline CCD, and we've driven a much higher dynamic range from it, about 25,000 to 1 from 6.5 micron pixel size. So that's a very attractive feature of the scientific CMOS as well. Now the Darkcurrent, I've actually highlighted the Sony interline. It has a naturally much lower Darkcurrent than CMOS. And I've highlighted that because it feeds into one of the application recommendations that would maintain for interline CCD technology. If you've got long exposure applications, you may still get a better result from an interline if the exposure is long enough, from a cooled interline, I should say. So let's just do a couple of comparisons. Let's take sCMOS versus interline CCD. So I'm showing here a signal to noise plot. So this is photons per 6.5 micron pixel area. And I'm showing it versus the signal to noise ratio. So obviously the higher the signal to noise, the better. So I'm using two technologies which have the same pixel size, so it's quite convenient to do a comparison this way. I don't have to then adjust for pixel size differences. What I'm showing here basically is the effective read noise. The upper curve is the CMOS, the sCMOS. The lower curve is the interline. At high signal levels, the two would converge. As you go to lower and lower signal levels on this logarithmic plot, the two curves would diverge, and that's the effective read noise of the interline pulling down the signal to noise ratio overall. So that was the theory. This was a practical measurement. This was done with a very low light, light-tight imaging rig, LED illuminating a resolution chart, and it was about 30 photons per pixel. And you can see on the same relative scaling the heightened read noise of the CCD. Similarly, on a CSU spinning disk, where again you're limiting the background, you can see the read noise effect of the CCD on a low light image. Now, when you compare to EMCCDs, it gets a bit more complex. So what I'm showing here is curves that show an Xon 888. Now, I've chosen this one for a reason of convenience more than anything. It has a 13 micron pixel size. Now, if you're going to do any comparison of a small pixel device and try to compare that to an ultra-sensitive EMCCD with a larger pixel, you're going to want, for reasons of signal to noise, to give the sCMOS the best possible chance, but also it's a realistic thing to do anyway. If you're down at these very low light levels, you're going to want to bin the pixels to improve your signal to noise. So that's exactly what I've modeled here. I'm assuming the sCMOS is 2 times 2 binned to give the exact same pixel size as an EMCCD, which has a 13 micron pixel size. So the photon flux at the bottom now is called photons per 13 micron pixel, and it gives a reasonably good overview then of how the technologies would compare in a low light scenario. So what you have here, bearing that in mind, so when you do a 2x2 binning of CMOS technology, the read noise doesn't stay the same. The read noise actually doubles. You're taking 4 pixels, summing the noise in quadrature, which is the root of the sum of the squares. It makes the read noise double, and that's been modeled in here. So with that in mind, you actually have a crossover point of about 50 electrons, just more than 50 photons per pixel of these 13 micron pixel sizes. So below that, while it doesn't look like a big range, is the low light range where a back-illuminated EMCCD would still offer better performance. So having had the camera out there for about a year and a lot of head-to-head demonstrations taking place versus EMCCD technology and in my own tests as well, my summation is that the majority of applications which had been purchasing back-thinned EMCCDs probably still have a reasonable justification to carry on using a back-thinned EMCCD. There's still a notable difference under these very low light application conditions, typified here by single molecule or even spinning disk confocal, where a back-thinned EMCCD can still outperform a scientific CMOS. However, from about 50 photons per pixel per 13 micron pixel upwards, you will get a better or similar signal to noise from an sCMOS, even though it's not back illuminated. The reason you have that crossover point, you might think, why does a single photon sensitive detector, which is back thinned, why does it ever have a lower signal to noise than a non-back thinned 1 electron pixel device, or 2 when it's binned? The reason is because of the multiplication noise of EMCCDs. As I mentioned, it has the effect of halving the quantum efficiency of an EMCCD, and that's why you have that crossover point. So again, that was the theory. This is the practice. These were measurements I did in a lab in Andor. I did them at a number of different photon intensities. Again, I have very good control over an LED LED attenuation and a light-tight imaging rig. I can very readily estimate the number of photons per pixel. So I've compared a 2x2 bin CMOS to a non-bin EMCCD, so the same effective pixel size, and it pretty much is in accord with the theory. You go down in intensity, at brighter signals you have very, very comparable signal to noise. If you go beyond that threshold, I'm showing here 8 photons per pixel, you still see a notably better signal to noise from a back-thinned EMCCD. When comparing technologies, you may want to consider field of view. Some applications require a larger field of view. You want to more readily capture the field of view of the microscope, or that the microscope has to offer. That's much more readily done with a 5.5 megapixel sensor. I'm showing here the CMOS versus the Sony interline. Now, I mentioned earlier that there can be a remaining technical reason, pricing aside, there can be a remaining technical reason to stay with a cooled interline CCD, and that's at longer exposure. So what I'm showing here is the noise floor. So that's, again, the read noise and the dark noise combined, the contributions of each noise source combined versus exposure time. So basically, when it's showing that when you go to about more than 1 minute exposure, there's a crossover point, and the combined noise of the sCMOS would actually get higher than the noise of what I'm showing here is the Clara, and it's 1 megahertz low noise mode. It maintains a very, very low noise because of the negligible dark current, whereas even a cooled sCMOS after 1 minute, you'd find that being problematic. So that's a technical reason to stay with interline CCDs for such applications. Very quickly, I don't want to spend too much time on this, but it's probably complete to consider a back-thinned CCD as well. So the point I'm making here, if you look at the blue curve at the top, if you read out a back-illuminated CCD very, very slowly, you will get a better signal to noise throughout all photon conditions if you're able to read out very slowly. If you're reading out faster, then there's a crossover point, and if you want to read out very, very, very fast, an sCMOS is the only way to do that. So when you're able to use 1 megahertz or 100 kilohertz pixel readout speeds, more in terms of seconds per frame rather than frames per second, you can still have a better signal to noise from a back-thin CCD. So just a couple of slides to finish off, just some general application guidance. From having had the camera out there for about a year, we've built up a reasonable view of what applications it's applying itself well to, being new technology, and what applications, for example, an EMCCD would still give a convincingly better signal-to-noise ratio and performance from. So single molecule detection, generally our summation is that you will still get, by and large, a better result from a back-thinned EMCCD for single molecule work. There are some exceptions, obviously, and there will be some applications that just need the speed and need to move over to an sCMOS, for example, or need a bigger field of view. But generally speaking, we've noticed you will get a better signal from at the very, very low light range from a back-thinned EMCCD. And don't forget as well, if you want to move to sCMOS, faster frame rates means shorter exposures and lower signals. There may be exceptions. There are some cases where you have brighter single molecule studies, for example quantum dots, which may well be bright enough for sCMOS. But bear in mind it's a huge generalization. However, again, generalizing, live cell imaging, we feel there's much more potential for sCMOS. There's greater flexibility in terms of the field of view, the resolution, the speed, the low noise, the dynamic range. So we feel generally for live cell imaging, sCMOS will be the new gold standard technology. There are some modalities which can still benefit from the raw sensitivity of an EMCCD. For example, here spinning disc confocal or some turf applications. And also you need to bear in mind sCMOS is the more cost-effective solution compared to an EMCCD. It's priced pretty much within the interline CCD price bracket, so that always must be borne in mind also, especially in these budget-constrained times. Super resolution I'm discussing here, more specifically the single molecule centroidic approaches of PAM STORM, or one of the various other acronyms. So what you really need for super resolution of this approach is sensitivity. It's a single molecule approach, so that goes without saying. And then you want a higher signal to noise because that determines your localization accuracy, in that it's related to the inverse of signal to noise ratio. You need speed because you have to acquire multiple images in succession and then sum them to generate an overall super resolved image. And then if you are able to go fast enough, that may in the future open up some abilities to apply it to dynamic process in living cells. However, bear in mind, faster imaging again means shorter exposures, reducing the signal to noise. That all must be borne in mind. Again, it's felt, and we've had some customers doing some head-to-head measurements in this field. It's felt again that at this point in time at least, while sCMOS may hold some longer-term potential, for example, when fluorophore designs become brighter, driven by this approach, it's felt that more at this point in time the back-thinned EMCCD still holds an overall advantage for this PAM STORM approach. One application where we have seen the sCMOS being applied very successfully to is SPIM, the Selective Plane Illumination Microscopy. So this is a technique which kind of decouples let's call it the confocal illumination from the objective. The illumination comes in as a sheet illumination from the side, and that means you can, since it's decoupled, you can do work with lower mag, larger working distance, lower numerical aperture lenses. So it's been applied, for example, I'm showing here a mouse embryo as being one of the typical subjects to which SPIM is being applied. So the key specs here have been resolution, field of view and speed, and the sCMOS technology ticks those boxes really, really well. It's less important to have the extremely low light sensitivity in SPIM. You tend to be able to apply a bit more illumination power because you're not illuminating down through the volume of the sample. You're illuminating from the side through a thin sliver of the sample, kind of analogous to turf. So there's less, you can get away with a wee bit more illumination in SPIM, so there's not as much emphasis on the very, very raw, sensitive attributes of an EMCCD. Dual wavelength applications, so there's a number of these. There's a couple of possibilities. In this case, Andor offer this device called the 2-cam, which is a dual camera splitter. It's very well designed for minimal pixel distortion, for minimal distortion between the different channels, very good pixel registration and very good transmission. So you do have that option. It's designed with a suitable aperture size that matches this very large sensor of the NEO. So you can put 2 Xons or 2 NEOs onto that, and you don't have to sacrifice the field of view of the sensor. You can apply a different wavelength, say, to each camera. So that's obviously the more costly approach, 2 cameras on a 2-cam. Another option is to use 1 camera, and what I'm recommending here is to make use of the very large pixel in the NEO, the very large resolution in the NEO, and use a dual wavelength splitter on 1 camera. So we offer this device called the OptoSplit, and it then splits 2 parallel fields of view, 1 for each wavelength on the same sensor. again, that's a fairly large aperture, quite well suited to the sensor size that exists in the Neo. So you're really taking advantage of that field of view capability of that camera. I'm very conscious of time, so I'm glad this is close to the end. So again, just revisiting the need sometimes for a CCD. I'm using the example of luminescence here. Say it's long exposure bioluminescence. You will get your best overall results. If you can take your time reading out, you'll get your best overall results from back-thinned CCD like the iXon camera. If you need to have that, if this is bioluminescence microscopy and you feel to have small pixels still, then you might be better suited to the interline CCD like the Clara, and it's certainly more cost effective as well. So as I said, you'll get better signal to noise ratio than the sCMOS with exposures that are greater than 1 minute. So this went on for an hour now, so I thank you very much for your attention and for hanging in there. I see the attendance is still quite strong, so thank you very much for that.
Thank you, Colin. That was an extremely informative presentation, and you have raised a lot of good questions from the audience. You can reach us with any comments or questions at webinar@photonics.com. This informative presentation from Andor Technology has been terrific, and we hope you will join us for the next Photonics Media webinar, The Future of Imaging, on December 14th, 2011. Thank you.